Hey everyone, I hope you can hear me. And welcome to this chargedUP meetup series from By Edition. My name is Csaba Kozak, and as Sudi already mentioned, I will talk about Kotlin Symbol Processing tonight. I will show you briefly the agenda of this talk. First of all, I will talk about some of the history of code generation in general, and also in specifically about Kotlin. Then I will introduce Kotlin Symbol Processing, why we need a new tool for code generation in Kotlin. And then I will show you how to utilize this technology with third-party or already pre-existing Kotlin Symbol Processing libraries. And finally, we will deep dive, and I will show you how you can write your own symbol processor if you would like so. So let's get to it. Code generation means that instead of writing the code by hand, you generate some kind of source code based on some other information. It is important that by code generation I mean that you want to generate source code and not compile code or bytecode, because that I would call compilation in this talk. And there are lots of different technologies to do that in all of the targets, all of the platforms, and we will see that there are multiple technologies in the Kotlin world as well. But why would you use such a concept like code generation to work on your code base? When we write code, there are a lot of tasks which are repetitive, boring, menial, and we write the same code again and again. I guess you all met this problem as developers. And if you use code generation, you can automate this task. It will generate all of the code for you, which you have to write by hand. And therefore, it lets you focus on more interesting problems, problem solving, higher level problems, and also the business logic of the application. Also, if you use a cool tool to generate code, it will always work the same way. It will generate the very same code base, so it will be consistent and standardized, and it will not make any mistakes because it's obviously it's a tool, it's not a human. And therefore, if you use code generation, you can make sure that even for the 100th time, it will generate the same code. Hopefully, it will be error-free. Also, when we talk about boilerplate code, I know we usually refer by boring, stupid code. However, some of this code can be quite complex and hard to write if you want to achieve optimal runtime performance or correct working. Therefore, if you write this code again and again, it is very likely that you will make some errors. And also, it is quite ugly sometimes if you write this kind of code. For example, if you think about writing a JSON processor or SQLite handling code, it is not the most likable code that you can write. But you can automate this again with code generation. And finally, if you think about on a bigger problem and you jump from just one platform, if you write applications which are targeting multiple platforms, I mean like which actually consists of multiple platforms like a front end and back end, and those platforms has to communicate, then it is a very good solution to use code generation to share code between them. For example, as I mentioned, in the backend and front end, these are mostly communicated using REST APIs. And if you define the models, how they should communicate in a high-level language, then you can generate controllers for the backend and client code for the front end for all of the target platforms without actually have to write all of these codes yourself. Let's see which kind of code generation technologies are available for Kotlin. The first one I mentioned here is KPT. KPT stands for Kotlin Annotation Processing Tool. I guess if you are familiar with Kotlin and Android, or just Kotlin in general, then you are aware that Kotlin was originated from the Java programming language, and at the first time its sole target platform was the JVM. Therefore, Kotlin could greatly benefit from the already existing Java ecosystem, and actually Kotlin has very good interoperability with the Java libraries and code. Java has this code generation technology called Java Annotation Processing, or APT, and this KAPT tool is a bridge between Java and Kotlin, which enables the Java annotation processors to run on Kotlin code base. It is a very useful tool because a lot of pre-existing libraries which were written for Java are very useful for Kotlin as well. For example, Dagger, which is a dependency injection library, it is actually a Java annotation processor. It was a Java annotation processor at first, and you could bring this library to the Kotlin code base using this tool. However, this tool has a lot of limitations. First and foremost, it doesn't understand Kotlin specific language concepts because it is a Java-based tool. It doesn't know about any Kotlin specific enhanced features like extension functions and the receiver of an extension function, or nullability, to mention a few examples. Also, it has a big compilation time overhead. Again, because this is a Java-based tool, first the Kotlin compiler has to generate some Java stubs, which then it can feed into this KAPT tool, and it takes a lot of time. So it is quite slow if you run these Java annotation processors in your Kotlin code base. And again, because of this is a Java tool, it only works on Android and JVM projects and not on multi-platform projects. And actually, it is being replaced. It is in now maintenance mode, and if I just check the official documentation for this tool, and it now says that you should migrate to Kotlin Symbol Processing, obviously. There is another tool in the Kotlin world for generating code, and it is called Kotlin Compiler Plugins. This tool runs during the Kotlin compilation process, and actually it is part of the Kotlin compiler, so you do not have to add any new dependency or any library or build process. This is a very, very powerful tool, and you can achieve any kind of magic if you use it. This is because it accesses all of the information of your code base, of the compiled code base, and actually it can run transformations on it, so actually modify your pre-existing source code and create something totally different which you originally wrote. So this is a very, very powerful tool, and it can achieve anything basically. However, it is very complex to write. This has several different reasons. I think the most important reason that it has a private API, which is undocumented, so it is not easy to learn it. And unfortunately, this API actually changes with every Kotlin version as well, so you have to learn it again and again and update your processors. Also, it doesn't emit source code, so if you write your processors, you don't emit or generate source code, but Java bytecode or low-level virtual machine intermediate representation code, so some kind of bytecode or compiled code. So you have to learn first how to understand and how to write code in bytecode, and then you have to generate the bytecode and not source code. So you again learn another language, a low-level language. This is similar to assembly. And finally, if you want to write a Kotlin compiler plugin which behaves well and is very user-friendly, then you have to first write the Gradle plugin which runs in the command line. But you also have to write an IntelliJ plugin, so an IDE plugin, which will run during code assistance, and you have to recreate the whole processor in IntelliJ as well. So when the developer writes the code, it can access the generated code in the IDE. So it is a quite how to grasp this tool and how to implement Kotlin compiler plugins. However, since as I mentioned, this is a Kotlin compiler. It's a part of the Kotlin compilation process. It supports Kotlin multi-platform out of the box. I brought you some examples because maybe you haven't heard of this tool before, but you already use some of the libraries which use this technology. The first example is now a deprecated one, Kotlin Synthetics. I think it was also called Kotlin Android Extensions. And I guess if you are an Android developer for more than like 2 years, then you have seen this code, this technology before. This was used to generate view bindings and replace the boilerplate code which you have to when you access the views using this findView by ID function. The second example is the Parcelize, which this tool can generate parcelable implementations, which is a serialization format on Android. Kotlin serialization, which is again a serialization tool. Mostly it can be used for JSON serialization, but it supports other serialization formats as well. It also was written in Kotlin compiler plugin. And finally, I think the most well-known example here is Jetpack Compose itself, which is the new Android UI toolkit, which is very similar to SwiftUI. It is again at least a small part of it, but a very crucial part was written with Kotlin compiler plugins, and this enables you to emit those UI nodes and create a tree without actually write add and tree and other kind of tree alteration functions in your code. Just a simple Kotlin code in Jetpack Compose code. And finally, I brought Reflection as well. So Reflection actually is not a code generation tool, and it runs at runtime and not at compile time like actual code generation tools. But it also it serves the very same purpose, or it can be used to solve the very same problems. It is quite easy to write because again it is running on runtime. You don't have to write a separate tool first to generate code. However, it is not type safe. It can break very easily if you update any of your libraries or anything else, since it doesn't access anything in a type safe manner. And also, if you are working on Android, you have to take extra care, because if you use obfuscation tool like ProGuard or Arrayed, then you have to make sure that this obfuscation won't break your reflective code. Also, Reflection has slower runtime performance. Historically, it was a very big penalty. Now it is not that big, but still it has some runtime performance slowdowns on Android compared to calling the code directly, like with code generation. And also, Reflection in Kotlin isn't available for other platforms, only for Android and JVM. So it is not multi-platform. So as you could see, we have a lot of different technologies, or at least 3 I mentioned here for Kotlin, but we can do better. Therefore, we can introduce this new tool, which is called Kotlin Symbol Processing, or KSP. Interestingly, this tool is not developed by JetBrains. It was created by Google. I guess they wanted to solve some problems which was very hard with Kotlin compiler plugins. Therefore, they created a new tool to solve some problems more easily. But it is a strange beast, because although it is developed by Google and it is under the Google namespace on GitHub, its documentation resides in the official Kotlin documentation site. So it is like between Google and JetBrains. And I can say it's a fun fact, but KSP tool is itself embedded as a Kotlin compiler plugin. So it's again a Kotlin compiler plugin which allows you to write easier or lightweight Kotlin compiler plugins. we can say that. Let's compare this technology to the previous ones. If we compare it to the Kotlin C compiler plugins, we can see that those are very powerful, but as I mentioned, those are tied very closely to the Kotlin compiler and sensitive to changes. KSP is one of the best abilities is that it has a very well-defined API, which is stable, and it shields all the sensitivity and all the nuances of the compiler from you as a symbol processor developer. And also, for the Kotlin compiler plugins, you have to have insider knowledge about the compiler, and you have to know the low-level assembly-like language. For Kotlin symbol processing, it is much easier to learn API, and it is you can learn it much faster. If you compare it to Reflection, actually we can find that its API is very similar to Reflection in the Kotlin.reflection package. However, there is a very big difference that in KSP, types have to be resolved explicitly, and in Reflection you can already access them without any manual type resolution, and therefore the two APIs are different, and we cannot share them between KSP and Kotlin Reflection, but still there are a lot of similarities. And if you compare it to KEPT or KPT, obviously Kotlin symbol processing has a very big compile time advantage, because it's not a Java tool. It doesn't need any Java step generation or error bridging. It runs directly in the Kotlin compiler, so it has improved build performance compared to the Java annotation processors or KEPT. As far as I know, there are some measurements, and I heard that at least 1.3 times faster. KSP can be faster than KPT. Also, it is not tied to the JVM. It is a Kotlin first construct, and you can use it in multi-platform. Its API is more Kotlin idiomatic, so you can use it in a more friendlier way. And it can understand Kotlin symbols like extension functions or nullability or state classes or objects or any other stuff, which is new in Kotlin and isn't available in Java. However, as all tools, KSP has its own limitations as well. It cannot examine the expression level information of the source code, so it can examine the classes, the name of a classes, the functions of the classes, the properties, the parameters of the function, etc. But it cannot look inside the function bodies at all. So you cannot check what expressions, what statements are written inside the functions. Also, it cannot modify the existing source code. It can only generate new constructs compared to Kotlin compiler plugins. And also, if you are Java annotation processing API developer, or you use Java annotation processing API, Pivot, or KEPT or Dagger, it is not 100% compatible with that. So you cannot just port your library very simply to KSP. You have to rewrite it completely. How you can use this Kotlin symbol processing in your own projects, in your own applications, without writing new Kotlin symbol processors. So I mean, when you have third-party processors which you want to include on your own project. Fortunately, Kotlin symbol processing support is now very widespread in the Kotlin world, and most of the used libraries are now supporting Kotlin symbol processing. I have a few examples here. The first library is Room. It is a database library for Android, and actually it is now, as far as I know, it is multi-platform, so it's also available on native platforms as well. And it is an ORM library, so you can generate the SQL statements from your Kotlin code without you have to write those SQLs. and it supports now KSP out of the box. Moshi is again a JSON serialization library which now supports KSP. Glad is an image loading library which has some code generation capabilities, and it also supports KSP. Coin is a service locator tool, so it's kind of a dependency injection. It works at runtime by default, but it has a annotations module as well, which enables code generation, and it's based on Kotlin Symbol Processing. And I think the biggest thing here is Dagger, which I mentioned. It was like most of these tools here originally written with Java Annotation Processing or KAPT. It now supports Kotlin Symbol Processing, both Dagger and Hilt, and the other Hilt libraries like Hilt View Model or Hilt Work Manager. They also support Kotlin Symbol Processing as well. But please remember, this support is now in alpha, so it is not production ready as far as I know. So you can try it out in your project, but you can expect some errors. If you want to include these libraries using this KSP technology, you have to do it like in this code snippet. As I mentioned, that KSP is written by Google, so it's created by Google. Therefore, it isn't available by default in your Kotlin compiler. You have to add another Gradle plugin, this com.google.devtools.ksp plugin. And this is very interesting because it has two version numbers. This is because the first version is actually the Kotlin version that you use in your project, the Kotlin compiler's version that you use. I mentioned to you previously that KSP has a big advantage over Kotlin compiler plugins because it's not tied to the Kotlin compiler. But now I say to you that you have to write here the exact Kotlin version. Why is this? This is because when you include the Kotlin KSP plugin here, you actually include the implementation of it. And that implementation is obviously tied to the Kotlin versions because it is based on Kotlin compiler plugins. But when you include the processors themselves, now those doesn't depend. Those do not depend on the Kotlin version. So if you bump the Kotlin version in your project, you have to also bump the KSP version here. So the 1.9.24, you have to change that, but you don't have to change the room version because that's now independent of the Kotlin version, thanks to this KSP tool. And it also has its own version number, which is based on semantic versioning. And you can also update KSP as well when it has new versions. And the same this KSP version, so for example 1.0.20 here has different kind of Kotlin versions. So there is a 1.8 Kotlin version from KSP for the very same 1.0.20 KSP version. I know it's very complicated, but you have to just remember that update the last version, the KSP version, to the latest, and keep the Kotlin version of KSP in par with your Kotlin compiler in your project globally. Then, in the dependencies section, you have to add two dependencies here usually. One dependency is a usual runtime dependency, which will be included in your project, your app. So therefore, you have to use this implementation configuration here. And then the most interesting part here is that you have to include the processor, or we can use it. We can also call it the compiler, and you have to include it with the KSP configuration. In the last block, which is optional, you can add some KSP arguments here, which will be passed to the processor, and based on your arguments, the processor can create different kind of code, obviously. The previous example was actually an Android project. Sorry for not mentioning that. As I mentioned, Kotlin Symbol Processing also supports multi-platform projects. And in this example, I will show you how to add Kotlin Symbol Processing in a multi-platform project. The plugins block is the very same with the previous one. You have to include the KSP plugin, and we did with this interesting versioning. And then, as with all of the Kotlin multi-platform projects, you have to add your targets and your source sets. In any of your source sets, you have to include the runtime part of the processor. For example, here I had coin annotations for the common source sets. And then, in the last part, which is the most important part again here, in the dependencies section, I have to include the Kotlin symbol processor, which will actually generate the code, which is the Kotlin KSP compiler here. It has this very strange dependency notation, because I don't write like KSP configuration directly. I use this add and KSP command main metadata configuration name, which is included as a string. This is because we can add processors for any kind of source sets. So for example, I can include a different kind of processor only for the iOS source set or for the Android source set. But if we want to run Kotlin symbol processors on the common code, then I have to write this KSP command main metadata, which we run on the common code, and it generates the generated code for all of the platforms shared. So this was the very brief example how can you include a Kotlin symbol processor which is written by a third party into your projects. And actually you can find this example also in the KPT migration, as I mentioned, which is now in maintenance mode. And in the last part, which will be I think the most bigger part, I will show you how to write your own Kotlin symbol processor. So if you have a no problem which you want to solve, some kind of special boilerplate code which you want to eliminate bar generation, then you can learn how to write the Kotlin symbol processor yourself. We saw this structure already in the previous slides. So in most cases, the Kotlin symbol processor takes part of two different modules. The one module is the runtime module, which will be included in the final application as well. We call this here annotations module because usually it will contain Kotlin annotations and only annotations, nothing else. The interesting part here, or the much bigger part here, is the processor module. The processor module will be included only in compile time, so it will not be included in the final application. It will not be added to the application or the APK, and it will examine the code base, annotation, and also the user written code, and then generate a new code. And I have a main project here. This can be an example project in your own GitHub repository, or a test project, or actually the final project of the user. And the user, as in the previous examples, has to include the annotation module as an implementation dependency, and your processor as a KSP dependency, which we run at compile time, and it won't be included in the final APK. The same diagram can be shown here as a build-gradle structure. So the annotation module is just a simple pure Kotlin module. It doesn't contain anything. Then we have this processor module on the bottom part. This has to reference the annotations module and also the Kotlin symbol processing API. And your main project has to include your annotations module and your processor module as a KSP in a KSP configuration. The entry point for processing is this Kotlin symbol processor interface. This interface has three different functions. The last two are not that important. They are hook methods. They are called either when the processing was finished, so the finish function, or when any kind of exception was thrown during the processing, and then this onError function will be called. However, the most important function here is the process function. This will be called in any processing round when the Kotlin compiler actually runs, and it will invoke your processor. And actually, this is the part when you can examine the code base, and based on that code base, you can then generate new code. To create your processor, you also have to implement this symbol processor provider. This provider will actually be instantiated by the Kotlin compiler, and then using that provider, then you can create or instantiate your own symbol processor. In that symbol processor, that you can you can create your symbol processor manually here, and you can pass any kind of parameters here, either from the symbol processing environment, which is passed to the create function, or you can pass your own constructor parameters as well to the processor. And this processor, which is created, it will be retained by the Kotlin compiler. So if you save any kind of state in it, it will stay there during the whole Kotlin compilation process. And how the Kotlin compiler will discover your processor. So not just the processor, but the exact class, the exact provider which will create your processor. This is an old Java service creation technology here. I forget the exact name, sorry. But anyways, you have to create this very long file, very long named file here in this very specific folder. And it has to have this concrete name here, and then the contents of that file should be your provider, the fully qualified name of your provider class, and the Kotlin compiler will look for all of these files which are named in such a manner, and they read those files, and then they can see the fully qualified name of your provider, and then instantiate your provider, and which then will create your processor. As you could see, the provider has a symbol processing environment parameter in this create function. This environment has several properties here. Options as a map, which are passed in from the Gradle, as we can see with the Rumi example. Also the code generator, which will be used to generate the actual code, the actual files. Also there is a logger here where you can add some compilation warnings or errors, or throw exceptions. And also it has several version information about the Kotlin version being used, and also the KSP version being used. And also it will have information of what kind of platforms you are targeting currently, so Android, iOS, native, or Linux. Kotlin Symbol Processing models your whole source code as abstract syntax tree, as with all of these other tools. All of these classes or interfaces which are the models themselves are prefixed with this keys string. So a Kotlin file will be modeled as a keys file, and it will have the package name, the file name, and all of the annotations. And then it can have 0 or multiple declarations. It can have classes or functions, top-level functions, or top-level properties or global variables. And in turn, also the classes can have declarations and properties and functions themselves. So it can be a recursive tree here, and the whole source code is modeled this way. So when you create a Kotlin symbol processor, you have to examine and inspect the code base based on these model objects which are created during the parsing of the source code in the compiler. I know that you cannot see anything from this slide, and it wasn't my intention to actually show anything here, just the complexity, because this is just a small or simple overview of the whole Kotlin Symbol Processing API. It has lots of different classes and interfaces which model the different concepts in the Kotlin programming language. If you zoom in, maybe you can see a little bit, but on the top there is KS node interface or class, I don't know, maybe interface. Yes, all of the model classes will inherit from that, and every Kotlin programming language element will be represented as a KS node. And on the left side, you can see there are a lot of reference kind of elements. These are used when you reference different kind of types or any kind of types from your code base. For example, when you reference return type from a function. Sorry. And this is very important in Kotlin Symbol Processing, because maybe I mentioned this before, that in Kotlin Symbol Processing you have to resolve this type manually. So when, for example, when you have a return type of a function, you cannot inspect the fully qualified name of that return type of actually it is a class or an interface, if it is a class, if it has what kind of properties and functions it has. So you can only see very limited information from type references. And if you want to access the full information, you have to call this type reference.resolve function, which will resolve the type reference to a full type, and then you can access any kind of information. But this is a manual call. The sole reason for this is not to overcomplicate the API, but to make you understand that this is a costly operation and you should avoid it as much as possible. And you can add some filters to your symbols and only resolve the ones which are really interesting for you. So the reference has a reference name property, which is the very same name which used to reference, for example, a class in the code base, and when you call a class or when you instantiate the class, for example, using the constructor, and you check that simple name, which won't be the package name, which won't include the package name, so it's not a fully qualified name, only the simple name of the class. And if it's not a name which is interesting to you, then you can go on and not resolve it. However, if you resolve it, then you will have this type interface, which will include all of the information about the type, whether it is nullable or is it mutable, or you can get the real or the actual declaration of the type, which will include all of the things which are written in the code base about that type, so functions, properties, modifiers, everything else. And if you go to the right side of this big diagram, you can see the declaration part of the models here, and that these will contain all of the information about the Kotlin source code, or the concepts or the programming language elements which you can examine, and then based on those elements you can generate the new code. I brought you a very simple example here, which and based on this example we'll write a very simple processor. So the goal here is to create a builder class using the well-known builder pattern. To achieve that, we'll create our own annotations, which is called very simply builder or add builder. And if we add this onto a class, then we will generate a builder class, which will have these builder functions like with-A, with-B, with-C, and also a final function which will actually instantiate our original class and return the object from it. This is a very well-known pattern, and this could be this repetitive and boilerplate code can be automated by code generation and KSP. In order to achieve that, in our process function, we have to first get all the Kotlin symbols that are annotated with our builder annotation. To achieve that, we can call this resolver.getSymbols with annotations function. Then, just to make sure, here I filter for all of the classes. So I filter out the functions or properties or files or any other elements that are not classes. And then I will process all of the classes which are annotated with this annotation builder. My goal is to generate a builder, so I will get all of the properties of my Kotlin class. But to do that, I first have to get the constructor, which will contain all the parameters. To illustrate how we can use this logger, I added an error check here. So I will log a compilation error here that the user added this annotation, builder annotation to a class which doesn't have a primary constructor. And I also include the location, which is the class. So when the user run my processor, the Kotlin error will actually be printed on that class. Otherwise, you can get the package name and the simple name of the class, and we can generate that builder class later. And also, I will iterate over all of the parameters of the class or the constructor, and we get the name and the type of all of the parameters. Here, remember, I have to resolve the actual type to get the qualified name. So the full name of the type, which type the parameter is. And then I can append those builder functions and property holders in my generated builder class. KSP supports multiple processing rounds. This is needed because it is possible that there are multiple Kotlin symbol processors in one project, and users can reference classes and types and anything or functions which are not yet generated. And when my processor runs into this kind of types, then it will have an error. But it can let it go and defer generation to a next round. So if we run into a type which is not yet created, not yet generated, we will say, okay, let's go to the second round, and hopefully in that round somebody will generate that type. To implement this, the process function can be used to return the default symbols. And you can use this helper function ks.notValidate to validate your symbols which are interested in and check whether those are already generated or not. This validate will actually resolve the types. And when you, in the next round, this get new files will return only the files which are generated since the previous round. To achieve that, here is a very simple code example. Again, I get all the symbols annotated with my builder annotation, and I will filter for all of the symbols which are valid, and I will only process the valid symbols. Then I will return the symbols which are not valid and defer them to the next processing round. And in the next round, in the resolver.getNewFiles, I will get all of the new generated files, and I can generate the new generated code based on those new files which are generated by previous symbol processors. But how I can generate the actual code? Because in the previous examples, we could only examine or inspect the code. How we can generate the Kotlin source code? To use that or to do that, you have to use this code generator interface. This code generator is passed in the environment, as we could see, and you cannot just simply create new files. You must use this code generator interface to create files which the Kotlin compiler know about. And how you construct the Kotlin code base is up to you. You can use that string builder or just string concatenation methods to create your generated code, which can be easy if you generate simpler code. But if you have lots of dynamics in your code base or a processor, then maybe you can use a library for that. And the Kotlin Poet library by Square is a code generation library, and it can generate code dynamically. Also, it has great interrupt with the KSP and helper function to write out the generated codes to this code generator KSP interface. Again, we have this very simple example to create a builder class from the original annotated class. I will just repeat it if you remember. And to continue our Kotlin symbol processors, we can add the code generation here. So first we'll generate the class using this typespec class builder. We will add the builder class name, which is the original class name, and we append the builder here. Then we will iterate over all of the parameters, and then we will generate the functions, the builder functions, which has this with prefix and the parameter name, and then we can add the properties which will hold the state which is passed to this with functions. And finally, we can generate the build function, which will invoke our constructor of the original class and pass all of the properties saved from the with functions. And the most important part is at the bottom again, when we will write out the generated code base to a new file, and the Kotlin compiler will know about it, and that will compile that generated source code. And this is my last slide about incremental processing. So Kotlin Symbol Processing supports incremental compilation and build. Incremental build means that if you built the project previously and you make some changes and then you build it again, if incremental build is enabled, then only the dirty or changed files will be recompiled, not the whole comp paste. KSP fortunately supports that, but in order to make it work, you have to mark every generated output with the and identify the original input sources corresponding to these generated outputs. So when those corresponding inputs change, then the outputs will be deleted and regenerated. And there can be two kinds of incremental methods. One is aggregating, when multiple inputs are used to generate one file. If you think about Dagger, that's aggregating processor, because when they're generating the graph, which is just one file, it will use almost all of your code base. And the isolating mode is the other mode, which is, for example, my builder processor, which I had shown previously here, is an isolating processor because only one input, the class, is used to generate the builder class. Again, Kotlin Poet has great integration to implement incremental Kotlin symbol processors. If you add this add originating KS file to the fastpaths builder, then you are done basically, and you created an incremental Kotlin symbol processor. And thank you very much for your attention, and this was my talk.